So we changed the course to an online course, and the idea is to have each day 1 to 1.5 or 2 hours lecture, and which is mainly focused on you asking questions. So you basically expected, not today, but afterwards, to read the slides beforehand and to try whether you can do it beforehand. Then in the lecture itself, we will concentrate mainly on the exercises and on the projects, and you can ask any questions where you had problems with. Good. So I want to start with the introduction to cement chemistry, because I want to be sure everybody is on the more or less on the same level on cement chemistry. And I promise tomorrow we will really start with chems. If we speak about cement, then we first should think shortly about what is cement. Normally we speak about Portland cement. Portland cement is produced by burning limestone and clay or sand at around 1450 degrees Celsius. It's ground afterwards, and we add gypsum to obtain something like an ordinary Portland cement. I'm sure many of you, or maybe some of you already have seen how they are burned. You have these very big ovens with a high temperature inside. And we use this high temperature because we need it to make halite at above 1400 degrees. Another thing which is quite important to know about cements is cement is responsible for 5 to 8% of man-made CO2 emissions, and a part of this emission is because our starting material, the calcium carbonate, contains CO2, which goes up into the air while you burn your cements. And this is more than half of the CO2 emission caused by cement production is actually because of this calcium carbonate or limestone we use in the production. And now some very simple general things about cement. When we have a cement paste, that as I just explained, it consists of clinker and gypsum or anhydrous. We add water, we get cement paste. If we add sand, we get mortar. If we add gravel, we get concrete. And if it then hardens, we can look at it and we get a nice picture like down here, which is a polished section of concrete. If we look on the composition of cements and concretes, we can see they are mainly dominated by the presence of calcium oxide. They contain around 20% of silicon dioxide, as well as 3 to 5% of iron and aluminium oxide, plus a number of other elements. The main phases we have in cement is halite, as well as some amount of belite, aluminate, and ferrite, which is here noted in the cement shorthand notation, which you will see afterwards in many of the slides. Here I have a slide with the main chemical reactions, and as said, halite is our main clinker. If we add water to it, it will react to CSH and Portlandite. And again, I have used here cement shorthand notation, where C stands for calcium oxide, S for SCO2, and so on. For the aluminate, we make mainly ettringite, which we also call AFT, or we can make some AFM phases, such as monocarbonate or monosulfate. And now I want to share with you a video made by 2 PhD students originally at EPFL, and it gives, I think, a very cool and very short introduction about what cement chemistry is. In case you want to watch it yourself in a complete version and you somehow manage to get access to YouTube, that would be the link to see it. Maybe just to get back to a bit more scientific level, if we look on the changes during the hydration of cements, we can follow it by a number of different methods, for instance, by TGA, thermogravimetric analysis. And one thing we start to see, we bind more and more water, because basically with TGA, we measure the water loss on a solid phase by heating it, and the more loss we can observe during this heating, the more water we had initially present. And we can see the presence of different minerals. For instance, here at the weight loss at 450, the presence of portlandite. And the early weight loss, we see the presence of ettringite as well as some CSH. And here we see the disappearance of gypsum and hemihydrate during the reaction. We can follow the same thing by using XRD. And the thing we can see is here we have all the signals of the clinker phases. We can see that they disappear relatively rapidly within the first 1 or 2 days, and that we start to form new hydrates, for instance, ettringite here, portlandite, CSH, which we cannot well see by XRD, as well as some AFM phases where we have the signal here. And we can quantify these changes, and basically we get the same image, a fast reaction of alite within the first day, also of most of the other clinker minerals, and production of portlandite and ettringite and other phases. We can look on pictures, and this is hydrating cement after 6 hours. It's a polished surface, and we can see here the unreacted clinker in light colors, and we can see that already after 6 hours we have a rim of hydration products around the cement, and we also start to see that they start to be interconnected. And actually normally around this time we start to observe setting in cements, basically the development of a first strength. And the black parts are the pores. We also can look on broken surfaces. This is again made with a SEM, but on a broken surface after 24 hours. After 24 hours, 1 day, most of the cement is connected now, and we can have a closer look. We can see here the structure of CSH, which looks a bit like a hedgehog. We can see in other places the formation of some portlandite. Portlandite is normally typically makes hexagonal flakes. And we also could see somewhere ettringite, which makes this long widths. And if we go here closer, we can actually see here the unreacted clinker. There's a gap, and then there's the hydration shell forming on top of it. So I guess up to now, this most of you will have known. However, we don't only have a solid phase, we also have a liquid phase because we add water. We can look on the liquid phase, basically what we normally do if we want to do that. We hydrate the cement in closed vessels to avoid that it dries out. And then we put the inner part of the vessels, naturally not the plastic, in a big steel die. And we put that on our biggest press we have in the lab. And if we do that, you actually can press out water of the cement, and you can go on to analyze it. And if you analyze it, you normally typically see a picture like that. This is the measured concentration in the solution we pressed out. We can see a high calcium and sulfate concentration up to maybe half a day. And later we see a decrease of calcium and sulfate. This is due to the depletion of calcium sulfate. We also see that in particular at later ages, the composition is dominated by sodium, potassium and hydroxide. And this composition is responsible for the very high pH we have in such system of the pH of around 13 to 14. The concentration of silicon and aluminium are relatively low. It's below 0.1 millimolar. The same is true also for the other elements we might have present, like magnesium or iron. They normally cannot be measured. And this picture you will see in general for all Portland cements. We can use all the knowledge we presented here also to model the changes during hydration. Basically, what we need to model, we need a model to describe the slow reaction of the clinkers, because you've seen they do not react immediately and also not very fast. And we need thermodynamic data to predict which kind of hydrates like CSH, portlandite, ettringite might form. And we can do this prediction by thermodynamic modeling. We need a thermodynamic database, and this is one of the things we will speak in the next 2 weeks a lot about. We have a general thermodynamic database, which we, in our case, we take from PSI NAGRA, and then we have some specific databases where we will come back to it in a lecture later this week. We need a model to follow the reaction of the anhydrous phases. There is a very simple one from Parrott and Killow, and there we need as input only surface area, water cement ratio, and composition. And we will also come back to that later this week. We can model the composition of the pore solution. This is the modeled composition, and we can compare it to the measured composition, and you can see we are able to predict what we are doing. And we hopefully will learn how to do that together. We also can model the composition of the solid phases, and there we predict the reaction of the clinker phases. I show here just the aluminium containing hydrates. As the aluminate reacts, we also, the gypsum will react, and we start to form ettringite. At later times, we might start to form an AFM phase. It will be monocarboaluminate if we have calcite present. If we don't have calcite present, we might form monosulfate. At the moment when we run out of gypsum, we cannot make any more ettringite because we are missing the calcium sulfate part. We also can model calcium and silicon hydrates. There we predict the formation of CSH, we predict the formation of portlandite, and again the dots show the measured data, and naturally we also predict a decrease of the amount of pore solution because the water is bound in the solid phase. We can model or express that also as a function of volume, or still a function of time, but volume based. And then we also start to realize why cements develop some strength, basically because, or one of the reasons is that we just increase the volume of the solid phase during the reaction as we put water from the pore solution into the solid phases where they can contribute to strength. Another interesting thing is also what I have put here in green is the so-called chemical shrinkage. And the chemical shrinkage basically says that the total volume of the system, water and solid, decreases as hydration continues. And this decrease of total volume is because the volume of water in solution in water is bigger than the volume of bound water. So water in a gypsum or in a CSH will have a slightly smaller volume than if it's in solution. And this causes the so-called chemical shrinkage. We also can compare our modeling with experimental data. I show here again an XRD, and we can see here the hydration of a Portland cement without limestone in this case. And then we predict the formation of ettringite monosulfate. And in fact, we see at longer times ettringite and monosulfate both present. If we do the same set of calculation for Portland cement which contains some calcite, we predict in this case the formation of ettringite monocarbonate instead of monosulfate. And in fact, again, that's what we can see by our XRD analysis. And we will also come back to that later, but we also can use thermodynamic modeling to predict what happens if we change one parameter of our cement composition. So for instance, we can predict the influence of limestone on the volume and the hydrates in a hydrated Portland cement. And you will see here, and we will come back to that example later in the course again, if we don't have any limestone, we might predict only monosulfate. If we have limestone, we predict monocarbonate instead, and this also stabilizes ettringite. This is important because ettringite, it contains a lot of water, and it also means it can generate a large volume. Now, if you look on the volume, you can see there's an increase of volume, of the total volume, from 0 calcium carbonate to around 2 or 3% calcium carbonate. Now, it's around 7%, and you might ask yourself, why do we think that's important? We think it's important because the total volume of solids you have in a hydrated cement is often mirrored in the compressive strengths or also in other strength properties afterwards in that cement. And this is an example of measurements of different Portland cements, mainly on the strength after 28 days or longer, and you see the same behavior as we predict by modeling. And again, I show you the data, but it's the same as we've seen before. Monocarbonate if we have calcite, monosulfate if we don't have calcite. Limestone also has more effects. It also affects the solution. If we have limestone, we have higher sulfate concentration and we have lower aluminium concentration than without. And I'm not sure whether I show you here the slide, but this then affects the kinetics of supplementary cementitious materials like slag, for instance. We can also, if we have other cementitious materials like blast furnace slag or fly ash or metakaolin or whatever in the cement, we can also amplify the limestone effect we've seen before, as shown here on a Portland cement fly ash systems, where we have, in addition to the Portland cement, around 50% of fly ash and some limestone. And you can see here that we have a bigger volume increase because we have more aluminium from the limestone, from the fly ash in the system, and this also results in a bigger effect of the limestone. So we can gain even more strength if we add limestone to blended systems. Maybe just some short conclusions. A Portland cement has a high pH, it contains a lot of portlandite, it has a high calcium to silica CSH. If we add limestone, we can have a positive effect because we form ettringite monocarbonate, and limestone can accelerate slag and halide reaction because it lowers aluminium concentrations. Now, this was my very short general introduction. Are there any questions to that? Just put up, just speak or put up your hand, whatever you prefer. No? Everybody happy? Everybody happy. If it's like that, then I think I would love to make everybody opening GEMS and do one simple thing. So thank you. So before we start, did everybody install GEMS? Put up a sign or put the comment if you do. Maybe those who did not manage, put up a sign. Mm-hmm. So everybody had installed GEMS. Did everybody install the cement database, the same data? No problems.
There is one question.
There's one question. Yes, please go ahead.
Okay, no question.
Oh, yes.
Okay.
Good. Then I think as we were relatively fast, I really would love to share with all of you first exercise. And what we're gonna do is I first share my screen again. If I manage. Yes. I want to open all of you together a new project and see whether you all manage. Because if we do it that together, then if there's any problem, we can solve it until tomorrow. I hope that's fine for everybody. Mm-hmm. So all of you, we will go now to open GEMS. At least if I manage to do it while we speak. GEMS, you will have, normally you will see somewhere a little button down here where you can open it. And it should look like that when you open it. Anybody who has problems just tells me. Good. Then we have two buttons here. This is always going for database. This is going for calculations. So I can press on this one to get a calculation or to start one. Now I want to make, you will have much less here than I, because I use it, so I have already a lot of all these processes. So I will want to make a new project. So I select new project. We call it C3A. 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 I have to call it 2 because I already have so many C3As. So it's not easy to do. Now I have to look on my slides. Then you can call it my first project, or you can call it course 2020. It doesn't matter. It's a comment. The only thing you should always consider, do not use any special signs. So no Chinese signs, no exclamation points, no things like that. And GEMS prefers to have not empty space. It also works with empty space, but it can sometimes make some problems. And the third thing, don't choose too long names. There's a limited number of characters you can put there, and yeah. Then you come to the database. You will see a PSI NACA, and as I said before, that's our general database. So we keep it as it is. We see third party, and depending on the installation, you might see some data, you might see some others. We want to select the same data. That's the cement database. And if you look on that, you see one which is called AAM and one is called PC. AAM stands for alkali activated material, and we do not need it at the moment. It's just in case later you want to calculate alkali activated materials, you will have to select that. You also have to open PC, and you will see that there's a number of different options for CSH. CSH, if we look in literature, there's a number of different ways to model it. And we've given the user the option to select himself which one he wants to use. For the course, we will always use the CSHQ. We will explain this model on the day where we have the lecture on the database, and at the moment you just have to know that you should always select the CSHQ. Maybe also a word of caution for later. Only select one CSH, else you make a big chaos, because there cannot be different CSH. It's just the selection of the model you want to use. The rest you do not necessarily activate. Subscript is another database, and support it, we don't need it. Any questions so far? No? Then we go to the next, and there we see a periodic system. We want to calculate something with calcium and aluminium, so we select calcium and aluminium. We want to calculate the effect of calcite and sulfate on it, so we also select C and S. And at the moment, if I'm not mistaken, we don't need the others. If you open, you always will see H and O is selected, because we assume that we normally have some water in the system. If you look closely on the periodic system, you will see here we have a N, a nitrogen, and we have a second nitrogen here. The reason for that is that this nitrogen over here is air nitrogen, N2, as we have, I think, around 70% in our air, 78 if I'm correct. Why do we have it twice? We have it twice because basically the nitrogen and the oxygen, thermodynamically, they should react to NOx. However, in reality, luckily this does not happen, because we would need a catalyst for, I cannot say the word. Anyway, it's not the reaction that happens directly. I want to see the chat. Problem is, okay, so I just also, Jianming said, please ask question. If you have any question, don't be shy. It's what we are here for. I was with the nitrogen, the air nitrogen. It's, as thermodynamically, it would react to NOx. We just made a second nitrogen which does not react to correspond to reality. You will see later there's a number of moments when things do not react as they should. For instance, diamonds are thermodynamically less stable than graphite. But we all know diamonds exist, and some of you probably would love to have some. Also, we are thermodynamically not stable, but we still exist, so that's a good thing. But let's come back to that. We don't need the nitrogen in this exercise. I just wanted to explain to you. So you all should have selected H, O, S, C, R, L, and calcium. Then we press next. There we come to a number of different inactivity models. I think we had a slide on it, if I'm not mistaken. I switch to the slide. There's we normally select, or I recommend you to select the Helgason model with the common B and A parameter. And then to select here the CaOH data, the CaOH version. Basically, this is a inactivity model originally developed by Helgason, which is implemented in GEMS, and it's well adequate for cement. And I recommend you to use always this setup, except if you have a good reason not to use that. Any questions? No. You can, if you want to learn more, you can learn more details on it, or else you just press check and OK. And maybe before we do that, I also want to explain a bit why do we need activity coefficients. If we look on thermodynamic data, for instance on a solubility product, you see we use this funny parenthesis. And they say, or the solubility product of gypsum is the activity of calcium 2+, the activity of sulfate 2-, and the activity of water. The one of water we normally can neglect because it's near to 1. However, GEMS will calculate it. And the activity of a solid phase is always 1. This is by definition. So how do we get from concentration to activity? Because normally if you measure total concentration, but for the thermodynamic data, you need activity. This we do with the help of a so-called activity coefficient. And this corrects the concentrations, and there's a number of models for it, and it helps us to use one constant and then to correct the activity depending on the model we use. Now you might ask yourself, what is an activity? So there's one good example. Imagine you are in your home village or somewhere in the countryside and want to find your friend who's always also lives in the same village, and you meet on the central place. You will find him very easily normally because there are not a lot of people around. Now imagine that you want to meet your friend in the airport in Beijing at rush hour or at the metro station. Let's go to central metro station in Beijing. There, even if you and your friend are both there at the same time, it will be very difficult to see each other because there's a lot of different people around. And basically it's the same thing for ions. If there's a lot of other ions around, it will be very difficult for them to see their friend. So for instance, for the calcium, it will be very difficult to find the sulfate. And the degree of difficulty we actually can express by the activity coefficient. Clear? Good. And just a bit more of theory. There's a number of different models you can find in literature. One is called Debye-Huckel, the one which is applicable at low ionic strengths, so it's not good for us. But there's an extended Debye-Huckel where E is for ionic strengths and the rest is some parameters. And there's one from Helgason, the one we've seen before, which is thought to be applicable below 1 to 2 molar ionic strengths. And this is the one we normally use, also because there are specific models for CaOH and NaOH solution, which is important for our systems. If you go for very, very high ionic strengths, you might want to use something like the SIT, specific ion interaction theory, or even a pizza coefficient. However, this is mathematically and computationally much more expensive. So in most cases, we just suggest to use this one. Now, after you've seen all that, let's go back to GEMS. Basically, I told you I want to have the Helgason. I want to have CaOH because we've seen that's our dominant ion. And if you look here, courage is the last of the list. And if you want to have an easy life, just select the last on the list everywhere. And then we can press check. Everybody there? Any problems?
No, for now.
Please just speak up. I don't see the...
No problem.
All fine. Okay. Then if you want to learn more, there's always the option to get here some help. However, this help, it's sometimes a bit challenging to understand. It's always everything there, but often you have to read it several times and very carefully to understand what it is meant. So that's also one of the reasons why we do these workshops. Then we press OK. Then it will, we are now in the modeling system. It will ask us to get a name of a system. Again, no special sign, but we want to calculate the effect of calcium carbonate. It will ask for not a number, normally we leave a 0. It will ask for the volume of the system. Again, if we don't have any constraint as here, we leave a 0. It asks for the pressure. 1 bar, that's atmospheric pressure, that's normally what we select. It will ask for the temperature. That's important to put in the proper temperature because you cannot change it. Or you have to make a new calculation if you want to do it at a different temperature. So now let me see what I've put here. Here we put 25 degrees. And I can see we wanted to calculate calcium sulfate, not calcium carbonate. So I rename it here to calcium sulfate. Everybody there?
Yes.
Then we can press OK. And then we basically did our first system. We can put here a comment. And I recommend you to use the commenting function because in a few weeks you will not remember what you have done or why you have done it. Here we can select what we want to have in our system. We want to have C3A, calcium aluminate. We want to have water, which is called aqua. And we want to have a little bit of calcium sulfate. And now I have again to check in my slides. In my slides, we said we need 5 grams of C3A, 2.25 grams of calcium sulfate, a little bit of calcium oxide plus water, and see what's happening. So that's what we're going to do. So in our experiments, we had 50 grams of water. We had how many calcium aluminate? 5 grams. And you can see I have here the units. So I always know what I put in. Then I have to check again. We have 2.52 grams of calcium oxide. And 2.5 grams of calcium sulfate, sorry, and 2.5 grams of calcium oxide. And then we often, or I recommend you to put a little bit of oxygen into it. Okay, why do we put oxygen? Because if we do thermodynamic modeling, it takes into account all kinds of redox reaction. And most of our experiments, if we don't work with slag, will be carried out under oxidizing condition. So it's easier just to give the system a little bit of oxygen. It also avoids that due to whatever reason, we might end up in anoxic condition. Any questions? Good, then you press OK once you have that. Oh, on the unit I haven't explained. You see here gram, or G stands for gram. You can, if you are unsure which units you should use, you can again press the help button and then you get to a dialog. And as we are here now at the compass, I can press to XA and then I have to press again on quantity concentration codes, and then I get a list of all the codes which are available. To be honest, normally I only use gram or moles and millimoles. I normally don't use the others because that's sufficient for what I want to use. So now I close it again. I press OK. I press check. That's always important to press check. This check, it's the green thing up here. It checks that we don't have any negative concentrations because we cannot have negative concentration, and it also checks that we don't have any zero concentration, and that's what it's doing. It said, oh, you had some carbonates. You said you will have some carbonates, but I cannot see them yet. So what do you want to do with it? Now I have to check what I want to do. In this example, I said, oh, maybe I will use it later, which I actually will. And then it just will add a very small amount of carbonate to the system. So I put an OK, check OK, check again. Now no more error. And then I can go to the red symbol, which means calculate equilibrium with chems. I can press it. It complains. It gives an error message. Our first calculation gives us an error message. That's not fair, but it's live. And this can happen. Maybe it happens to some of you as well. This has to do with the numerical settings in the program. And we just change it once. Maybe you have to change it the second time during the course, but it's very rare. We can change a number of things. I think the most important is this smoothing parameter, which sometimes is not where it should be. So what we're going to do, we're going to here to project. We put a small number on the smoothing parameter, 0.01. Then we press save. Everybody there? I found it down here on the project settings. You just change this one, press save, and then we go back to our single calculations and try again. And then it should work. Did it work for everybody?
Hi, Barbara. What is this parameter doing?
Sorry, I didn't understand you.
Yeah, what is the really the smoothing parameter to you? Added 0.01.
Okay, let's go back to the slide. That's easier to explain because it's already labeled everything. Or if you do a modeling program, there's a number of numerical settings you have to fulfill. So, yeah. For instance, you have a tolerance for inaccuracy, which is normally put to 10 to minus 5. If you have problems, we can increase that. There's a blue, here in blue, there's a parameter called minimum amount of stable phases. Normally it's put to 10 to minus 20. Anything That's below that will be ignored. We also can put that to lower amounts. And the smoothing parameter is a parameter, oh, I didn't explain it. If you, or basically what we do calculate here, we calculate the Gibbs free energy of the system. So it tries to minimize the energy of the whole system, because that's also what happens in reality. And to do that, it needs also sort of a smoothing assumption. And this can be 0 or it can be a very small number. It's one of the numerical settings in the model. And this is quite often to make problems. So we recommend just to put it 0.01 normally.
Okay. Okay, thank you.
You're very welcome. Now, did it work with everybody for the calculation? Anybody where it didn't work, please speak up. Good. And let's go back. And if you see here, we can see now the results on the, if we click on the sys-ec, that's system equilibrium, we can see the results. We can see solution. We have a lot of solution. We see activity, we come to that much later. We see some gas. Maybe we look on what's hidden. If we look on the solution, we see a whole speciation. We see aluminium sulfate, aluminium 3+, aluminium minus. We see calcium 2+. If we concentrate on the calcium, you can see we mainly have calcium 2+, you have a little bit of calcium hydroxide, and so on. And so we can see all these parameters. If we go to the gas, we can see we have a number of different gases, a little bit of CO2. We have oxygen, because we have put oxygen. We have basically no hydrogen, because we were oxidizing condition, and we have a little bit of water, or water damp in the gas. We have ettringite, and we will come back to that later. You can see here 2. A 2 means it's a solid solution. And if we look on the details, we have 2 ettringite, one which contains 32 waters and one which contains 30 water. We will come back to solid solution much later. We see some hydroxy sulfate AFM phase, that's a monosulfate. We can see we have a lot of portlandite. And that's it. That's all what we have. So I have to. And if we summarize what we have, we can see that easier on this slide. We have the name of the single system. We have 2.5 molars aqueous phase. We have a little bit of gas because we put the oxygen in it. We have 0.01, a little bit of ettringite, quite a lot of monosulfate, and also quite a lot of portlandite. And this is about the solid solution, which I already tried to explain. And we also can see the relative composition of the solid solution. A lot of 32 ettringite, less ettringite with a little bit of less water. There's also something which we call non-ideal solid solution. And again, this we will come back and explain later this week in some on the lectures on databases. There's also something which you could easily deactivate because normally we don't form it. I think I want, oh no, there's some more information. If you look at the bottom, you also can see that some general information like temperature, T in Kelvin, the pressure, 1 bar, the total volume of your system, the pH, the PE, that's redox, redox potential, and ES is ionic strength. So 0.05 is the ionic strength. Any positive PE means it's oxidizing condition, and the pH, you all know what it is. We can look on the detailed results if we click on this one, and I change back to GEMS. And we can see the details results here. You have a number of different sections. First one is called EQIC. This means equilibrium ionic concentrations. And the most important part is back here. There you have total concentration. So that's total dissolved concentration. And as maybe you will not remember it, each time when you click on it, you get explanation sometimes next to it as yellow, but you always get it back. It goes away when I want to show it. You always get it on the lower edge. You can see MT00, output total dissolved molarities of independent components in equilibrium state. In simple words, this means concentration. So if we look, for instance, for calcium, we see a value of 0.02. And as this is given in mole or molarities, this is 20 millimoles per liter. So we mainly have calcium, a little bit of sulfate and carbonate in our solution. We go back to this slide so I know what I wanted to show you. We also can look on the composite if we go to the second reader, which says EQPH. pH stands for phases, equilibrium phases. We can see which equilibrium phases we have. We've seen before the molar amounts, but on this screen we also can get the masses. So this is gram. We have 1.14 gram of ettringite. We have 10.8 grams of AFM phases because we have it 2 times, because solid solution is divided. And if we would go further down, much further down, we also see Portlandite. Maybe when you just might have seen, it can be challenging to go up and down in GEMS because we have like several boxes within each other, and you have two going up and down things, one on the outside and one here. We can compare what we got with experimental results. This is an example from Matcha, from Thomas Matcha in 2007, published in CCR and in his thesis. And there we see that he has formed monosulfate, portlandite, and very little ettringite, which is what we have predicted. If we go back up here, a lot of AFM, little AFT, some portlandite. The aqueous phases we already have seen at output total molarities. That's the logarithm of it. And here we have again a repetition of the input. So I will stop soon, because basically what you should do until tomorrow when you meet in the smaller groups, you should do the rest of it. That's also was the reason why I wanted to do that together. Did anybody have problems? Are there questions?
Professor Barbara, I have a question.
Yes.
When we see the experiment As are the experimental results, there are only one form of AFM, but in our calculations, we can see two forms of AFM. Why cannot see the other form?
Yes, that's a good question. Let's go back to that. I didn't explain it because there's a lot of things at the moment you try to understand at the same time. Basically, we have something which we call an ideal solid solution, like ettringite, and an ideal solid solution. Oh, what is a solid solution? We will explain that later again. But basically, a solid solution is a mixing from one solid with another. So if we think, I don't know, maybe on calcium sulfate or calcium carbonate, you could replace calcium carbonate as a simple form. You could replace some of the calcium by strontium. And this is actually working fine. And if you have this kind of replacement, we call it solid solution. Now, because it's 4 solid phases. Now there are minerals where you can replace all of the calcium in our example by the strontium. That's basically if you have aragonite, strontianite, you can make a complete solid solution, on the ideal solid solution. There are other minerals where you maybe only can put 10% strontium in the calcium, and then maybe 2% of calcium in the strontium member. And then you have entropy, and then you have something which we call a miscibility gap. And to mirror this miscibility gap, we need 2 definitions in GAMS. So what I wanted to say, the hydroxide sulfate AFM actually has a miscibility gap, which will be explained later this week. And to be able to calculate that within the program, we define 2 end members, one on the sulfate rich side and one on the hydroxide rich side. And that's why we have 2 end members for the non-ideal solid solution. But I promise it will be on the database lecture, there's some option to speak about that. Any other questions? Sometimes it shows invalid index of phases. What might cause this problem? Liming Huang, could you please share your screen? Show me your GAMS, or show us your GAMS, and so we can see when you get this invalid index of phases. Oh, yeah, press OK. Press OK. Yes. Let's just wait. Kommentieren. Okay. Maybe you press here. Yes. No, on GAMS. Now we see the slides. Oh, I see the slides. You cannot speak. Okay, but could you please share your screen again with us? I will tell you what you have to do. Yes. Please wait, I have to get my commenting. please press on C3A CaO. Yes, and then you go to the left here. So I can see, yes. And then you go to input system definition. That's basically this wide. You press on it. Yes, now we see the input. Now you go to the left again. But what I want to do, there are two phases which often make a problem. It's these two, this sulfate carbonate AFT. Make it to a zero, to a minus, sorry. And then you press the green one again to check, and then you press the red one. It's, if we have problems, then it's often the carbonate, the AFM phases. Can we see your screen again, please? Ling Ming Huang. Yes, I think what has happened, if we can, wait, I have to comment again, if we can look on your input, which we can find here. Yes? There is no carbonate in your input. Or when you, because you didn't press OK, you on the next slide, but you said no. That's fine too. But then that was the reason why we had the error on the carbonate solid solution, because the system wanted to check for the, so press OK here, that's fine. And then press the green button. Yes, last time when you pressed the green button, you didn't remember, you didn't put the OK for the carbonate, so you don't have carbonates, and that's why we had the error with the carbonate sulfate Edwin-Guide phases. Good. I hope this helps. Else discuss it with in the smaller course tomorrow, or try to do it again for yourself, making a new one, but this time activating the carbonates when you set up the system, and it should work. Good, I see here more question. There's Ming Feng Shu who wrote, there is something wrong with mic. I cannot speak. I cannot, okay, so maybe Ming Feng Shu, you have asked, where can I change the input of the calculation? I can show it. Oh, can you share your screen, Ming Feng Shu? Yes. Okay. Did you please first press the green button and then the red button?
This one?
Did you press first this one? You first have to do a calculation.
Okay.
Yes, and then you press this one. Okay. You had again the problem with, so we do the same trick as we did before. You have to change to C3A CaO to deactivate.
Which one?
To the one over here. And then we deactivate these two, and you have to select the input before to do that. Yeah. No, you have to change the side. You have to go to the other page up here. On the no, go to the top. Yes, yes. And now you can put here the minus. You also can type a minus.
Tap which one?
No, you can here, if you're on the plus, you just type with your keyboard a minus. It normally also should work. Yes, super. That's the reason why you have to do these things yourself, because it looks much easier than it is. Okay, now you press the green again, the green button up here, and then you press the red. You say yes. You press accept, and then I want to look on your input. I think there's something wrong. We check here your input. So the input as you get it from the yellow bottle, yes. I think you put a bit too much calcium. It was 2.53, wasn't it? Anybody can help her what she has to put in? Okay, you should have 2.52 calcium sulfate, 2.5 calcium oxide, and 0.1 oxygen. Oxygen you will find if you... Yes, exactly. 0.1. No, calcium oxide. It was calcium oxide. It's this calcium oxide should be 2.5. Yes. And oxygen should be 0.2, the last one. 0.1. No. Aluminium is 0. Yes, and O2 is 0.1. Yes, exactly. Now you check OK. Or you press OK. Now you check on the green. First the green, always first the green. Yeah, now it's looking better. Good. Annie, is it fine for you? Okay, there's also Bai Shuai Hit. That's a funny name. Who wants to know whether we model 100% reaction? Yes, at the moment we model 100% reaction, because anything we put in the input, GEMS will take as reactive. And maybe I share my screen now. And go to GEMS, to my GEMS. So if we go for our input and I put 5 grams in, everything will react. However, there are 2 versions to limit it. One version is just to put 4, so 80%, and then GEMS will only make 80% reaction. We can do that. But then you have to remember there's 20% missing because we didn't put it in the input. We can calculate, and the main thing is we will have less AFM and we will have now more Edwingite phases, mainly because we kept the amount of calcium sulfate constant. So we will have more calcium sulfate per C3A, and this favors Edwingite because Edwingite contains more sulfate than AFM phases. Did it answer your question? Good. Any other question? If not, then I think, are there?
Yes.
Yes.
In the chat.
There's a chat, sorry.
In the chat, there is another question.
Okay. Same phases calculate twice. I don't understand this question. Do you understand this question, Frank, or Bin, or Tsenguo?
But maybe Denk1 could somehow explain.
Ah, the hydroxide, the sulfate hydroxide AFM phase. This is because of the solid solution. We go back to my output. I share my screen again. And after. No, I want to do it here, that's easier. We go back to the solid solution slide. So, no, it's two. No, this one. Basically, yes, you already have it here twice. It's because we have this special solid solution with a miscibility gap. And then, due to practical reasons in GEMS, it occurs twice, and you just have to add up the results. So, like we do, for instance, here, we have AFM phases, we have mathematically it distributes it in both end members of the AFM phases with, in this case, the same weight. It doesn't have always to be, and then we just have to add them together, like we did here. So it's 10.83. And we will all discuss that in the smaller groups again on, I think it's on Thursday or Friday, when we speak about the databases. Any other comments? If not, I think I want to give you some last hints. You will see we already started with lecture 2, where we did a little bit of GEMS, because I wanted to be sure everybody had time and to be sure it works. And I want you to try to do all of them and see whether you can do it or not. There's a number of hints, and actually there's also all the solution would be in the next lecture in LO2B. However, I want to encourage you to do it without looking everything up. But naturally, you're allowed to look it up when you have problems. And also, tomorrow, you will do it together with your teachers in the smaller groups. And one of you actually will be asked to present it.
Yes, below we still see more questions. I think the first one is very specific, and the second one is again on the solid solutions. I think we can discuss this tomorrow in the groups, I guess.
Yes. Oh, yes. I think there's also it's for Bin and Tsenguo. There's some in the database lecture. There's a little bit about solid solutions, and naturally it's up to you to how you want to divide the different lectures. You can jump back and forth. And there was one question on thermodynamic simulation in magnesium phosphate cement. What we have, maybe this is also interesting a bit for everybody. There's a number of other databases. There's one for magnesium phosphate. There is a very recent one for zeolites, which just has been published by Bidmar, who sits there. And they all can be added to the cement database. Basically, you have to follow the same procedure as you did for the SEM data. First, close GEMS, then you can add the phosphate or the zeolite database or both, and you just can activate them or not activate them when you want to use it. The question we have here from Han Weiwei is that if I conduct thermodynamic simulation of magnesium phosphate cement, which B gamma should I choose? That's not so easy. It depends. When you have, if you have potassium, I would select the potassium chloride model. If I would have sodium, I would select the sodium chloride model. If I have none, then I would always select the sodium chloride model, because that's the most general ion activity model available. So basically you select it based on the main phases you might expect, or main solution phases, and if you have no clear indication, then always use sodium chloride.
Yeah, and the good news is that regarding the solid phases, there are not so many differences which model you choose. It's mainly if you're interested in the solution.
Yeah.
Sorry, I interrupted someone.
No, that's fine. That's fine. That's fine.
The person could repeat it.
Yes, and I think the last question is again about the solid solution, and it's not hydroxide sulfate, but it's carbonate ettringite, and it's the same thing. It has a miscibility gap, which we haven't explained yet, and that's why we have it twice in the database.
Yes, we'll explain it tomorrow in the second lecture, and there will, I think, because it's very specific, and then there will be some general information also in the databases lecture, so it will come at least twice.
So if there's no more, I wish you all fun in doing lecture 02 or doing the exercise for lecture 02, also in looking the exercises, and maybe also have a short glimpse at all L3, because we were relatively fast today. So, and we will just, if we are faster, we get a bit further, and if we are slower, then we get a bit slower. Any last comments?
So Barbara, talking for 2 hours is not easy, yeah?
It was only 1.5.
Yeah, but you see that our students, they start to warm up a little slowly, and afterwards they have quite many questions.
Yes.
It is, and I think it's also the reason why we make small groups. Yes, sorry.
Yes, and maybe tomorrow we might ask some of the students to show how they did the homework on the C3A. So it might be that some of the students will take up a part of the lecture. So
that's true. You will have more interactions since start from tomorrow, I think.
Yes. Yes.
Okay.
Then you all will get invitation by one of us. If anybody does not get any invitation, please contact us, including Xiangming, and we will see what happened wrong. And as already said, the lecture of Frank and me will be in English. Bin and Zhengmo will speak in Chinese or in English, as you wish. And
and also to our students, so you can download those slides from the website I have offered to you. And any one of you, if you want to upload things, you can also use the cloud. Mm-hmm. Okay.
Good.
Thank you very much, Barbara.
Thank you all. And Zai Qian.
We close today's session. Yeah. Frank, see you.
Yeah, see you tomorrow.